Okay, in this tutorial, I'm going to show you how to create a mesh for the geometry we created. In our last tutorial, we created such a cooler lying on the floor of this room, right? So we will need a mesh for this geometry. When you create a mesh, basically you may want to know where I need a mesh, where I don't need a mesh. Okay, the answer is very simple. Okay, wherever you need data, you need a mesh, because data come from solving differential equations. Okay, like Navier-Stokes equations for fluid flows, or the energy equation for the temperature values, right? For example, I need the temperature data in this cooler. So that means you also need to create a mesh inside the cooler. And because here this cooler is inside this room and is subject to heat transfer with the air inside the room. So basically we also need the temperature data of the air around this cooler. So we also need mesh in the room. Okay, so basically we need mesh everywhere. So when we do simulations in Fluent, we always have to at least provide three things to Fluent. First, mesh, as I have just mentioned, right? Wherever you need data, you want Fluent to solve for results, you need to create a mesh at such places. This is the first thing you have to give to Fluent, right? Mesh. Second thing is boundaries or boundary conditions. Okay. Your mesh always has boundaries, right? You don't have an infinite mesh. Okay, you only have a finite size mesh, which means it always has some boundaries. At those boundaries, you will have to provide boundary conditions, which means those data at those boundaries should be specified instead of being solved. Okay, otherwise solving those differential equations cannot give us a unique solution. Okay, you have to specify conditions at the boundaries of your mesh. This is done by creating those phase parts in ICEM. Okay, so if you find that you will need a boundary condition over certain surfaces, you will definitely need to create a corresponding surface part. Okay, so that eventually when we import such a mesh into Fluent, such part names will also show up in Fluent, so that we can assign different boundary conditions to those different surfaces. So this is the second thing we have to provide. Okay, that is boundary surfaces. Okay. Basically, in fact, here you may find that I define all the surfaces, right? I gave each surface a different name. Sometimes this is unnecessary, but I kind of feel that it's probably the best practice. So the third thing we have to provide to Fluent is zones. Okay, because in different places we have different materials, right? In this room we have air, in this cooler we have insulation first, then when we get into the cooler we have aluminum container, then we have some more air inside the container and some water here, right? So you definitely need to define such different zones in your mesh so that eventually we can use different types of materials in those different zones. Does that make sense? Okay, so so here in summary, okay, we need 3 different things: prepared and supplied to Fluent. First, mesh. Second, boundary surfaces. And my practice is that I define all the surfaces. And third, different zones. And here I'm going to create a mesh and at the same time creating the zones. Okay, and let's see how to do that. First, turn on the display of points. Okay, now you see all those points. Then go to Geometry tab. Then use Create Body. Okay, here this word body is basically identical to what I call zones. Okay, different regions, different zones where we will eventually apply different materials. Okay, so it's not a okay, anyways, let's create different zones. Okay. The first zone I'm going to create is the room air, which is this zone, right? The space inside the room and outside the cooler. So how can I define this zone? Here I'm going to define this zone by using the centroid of 2 points. So I select this point and this point. Okay, this point is on the cooler. Then I press the middle button. Okay, now you can see this zone is defined. Okay, although it looks like just one single point, but in fact it defines the whole zone, which is enclosed by the outer surface of the room and the outer surface of the cooler. Okay, so the whole space in between those surfaces is this new zone. Okay, you may wonder how ICEM or Fluent can recognize that this is the room air zone. Okay, how does it know that this zone in fact is from the outer surface of the room is in between outer surface of the room and surface of the cooler? It's very simple. Okay, we first create such a zone, right? You can see this is a point, and you should make sure that this point is always located in the zone we want to define. Okay, in this room, in this area, air region. Okay, then what happens is that later on when we create an unstructured mesh, then ICEM will directly put the first mesh cell here, then put the second mesh cell neighboring to the first cell. Okay, so basically this mesh gradually grows from this point outward, okay, until this mesh touches a surface. Okay, so the unstructured mesh will begin from here, and then it gradually grows, okay, expands and fills the space it can fill, any space it can fill until it touches a surface. So obviously it will fill all this air region until it touches, the room surface and the cooler surface, right? So this is how ICEM knows that this whole space in between the room surface and the cooler surface is one single zone. Okay, so this is my first zone, which eventually we will use air as its material. So basically we will need to define the second zone, that is the insulation zone, right? So zone insulation. Okay, any 2 points is fine, okay, as long as the centroid, that is the middle point of the line connecting the 2 points you select, should be located within the insulation zone. So I choose this point and that point, and make sure that this body point, this cross thing, this plus sign, is located in the insulation region. Okay, so the second zone, the third zone is air, but now this is not the air in the room, okay, it's not room air, it's air in the cooler. Okay, well, it's different zone. Okay, here you may wonder, well, since the air in the room and air in the cooler, they are of the same material, why should I define 2 different zones? The reason is because the zones are not only used to apply different materials, right? They also can be used to control the mesh density, right? I probably don't want very fine mesh in the air in the room because it's so big room, and the heat transfer and airflow only happens, very close to the cooler surface. So you only need fine mesh close to the cooler surface. You don't need very fine mesh elsewhere. But you may need very fine mesh in this air inside the cooler zone, right? Because almost every interesting heat transfer, relevant heat transfer happens here. So you want to define 2 different air zones. Okay. Again, you want to make sure that the body point is really located in the air zone. Okay, it's here. Okay, of course, if you want, you also can use like this point and this point, so that the body point is here. This is still in the air zone. Okay. Then the third one is water in the cooler. In fact, it's not just water. Okay, it's water in a plastic bag, but it doesn't matter. Okay, we only need to define this zone. Okay, so water in the cooler, right? And last but not least, we need a zone for the aluminum container. This guy here, right? Because it's a different material, it's aluminum. So you can see a container in the cooler, or aluminum container in the cooler. Aluminum container. Okay. use this point. Okay, make sure that this zone point is indeed inside the container region. Okay, that's pretty much all the zones we need, right? If you put all these zones together, that covers all the geometry, I mean all the space we have created. So the next step is to create a mesh in all those different zones. So here we first set up a global mesh size. So go to the mesh tab and use the first icon here. Here you can set the maximum cell, mesh cell size in this whole region, okay, in the whole space. Let me try say 1. Okay, see how big it is. Okay, this big. You may think, wow, that's big, that's huge, that's pretty much as big as a cooler itself. I totally agree, right? Which means, well, most likely I only want such big mesh, in those places far away from where the most interesting physics takes place, right? Which means you probably only want such big cells, in such places, right? Because heat transfer probably happens mostly around this cooler, so we need fine mesh here. But away from the cooler, for example, in this place, we probably can use such a big mesh. Anyways, this is a global maximum of all the mesh. Okay. Then I will, set up the mesh size. Set up different mesh size along different surfaces. Okay. For example, here I will first turn off all the parts. Then I will do each part one by one. Okay. I will first select the surfaces of the room, which includes the face of the floor. Well, I probably want to change its name. Face room floor. Okay, so room floor, room size, room top. Okay, if I turn on the display of the surfaces, you can see all the 6 surfaces of the room now are visible. So I can select all these surfaces. So I use, a box, a selection box, to include all the surfaces. They are all selected simultaneously. Then I press the middle button to confirm my selection. Then I select a different maximum mesh size other than my global maximum size. Okay, a global mesh size, a maximum size is 1, which probably is too big. I mean, I really want the mesh becomes finer when it goes closer and on those surfaces, right? Because typically the solid surfaces are the places where fluid flows and heat transfer happens. So here I probably want maximum size to be reduced to 9.5, and I want the height ratio to be as low as like 1.2. Okay, apply. Okay. So So I set up mesh size along those surfaces. Okay, so what happens is that when ICEM create such unstructured mesh, it will try to use 0.5 size mesh along such surfaces, and then gradually when it is away from those surfaces, it use bigger and bigger mesh, but it will never use a mesh which is bigger than 1, okay, because that is our global mesh maximum. Okay, that is a cap. Okay, in fact, at this moment you probably can see how the mesh looks like. Okay, you can push this compute mesh button, then push compute. Okay, now you can see the mesh. You can see basically the mesh size along those room surfaces, in fact, is relatively small. Okay, it's only 0.5. It is definitely not as big as 1, right? You have already seen how big a mesh with size 1 looks like, okay, which is almost as big as our cooler here. Okay, so here, if you want to see more mesh, not just those mesh on the surface, you can push this volume. Well, it doesn't really show anything. Zone room air, yeah. Now you have lots of mesh. Okay, it does not only show the mesh lines on the surface, but also the mesh inside the zone, which probably is not something I want. Okay, I just want to show you that right now we do have such mesh. Okay. Then I set up the mesh size for the other surfaces. Now I will go to the insulation, that is foam. Okay. Bottom, side, top. Okay. Now I probably want even finer mesh, right, for such foam region. So I don't use 0.5 now. This time I'm going to use like 0.2 probably. Okay, I'm not saying such maximum size is the best choice. Okay, I'm just showing you how to set up such parameters, and you will have to figure out the optimal mesh size by yourselves. Okay, so here 1.2 or 1. Even smaller number, but it has to be greater than 1. Okay, the smaller this ratio is, the better transition from the finer mesh to coarse mesh is. Okay, apply. Then we can redo the computer mesh and replace the old mesh with a new mesh. Okay, now you can see how it looks like. Okay, so this mesh, you can see in the insulation layer, its size is way smaller than the mesh in the room. See, you can see that. Okay, it doesn't. Okay, now it's better. See that, right? This mesh size is smaller. It's only 0.2, but on the floor it's like 0.5. Here it's like 0.5. Okay, so there is kind of a transition. See that, right? From the smaller 0.2 gradually grow to like 0.5. Okay, What else? Okay, don't worry about these pieces. Okay. We have already set up the insulation. Then we go ahead to set up all those pieces involving aluminum. Okay, so air. No, let's first set up all those pieces involving air. I mean air inside the cooler. Okay, so this is the phase between the insulation and air, and I also have water and air, and what else? That's pretty much okay. The only phases involving air. Yeah. Right. So then I select all these surfaces, and now I want to use like 0.1 for example, and ratio is 1.15. Okay, the smaller this number is, the better transition between different mesh density you have, but definitely it has to be greater than 1. Okay, it cannot be 1. It has to be at least like 1.01. Okay. Okay, then we redo the mesh. Now we have lots of finer mesh. Okay. Well, not that fine, but still pretty fine. You can see the difference. Okay. So here is 0.2 and here is only 0.1. Okay. We have already set up the mesh density for the room, for the foam, for all the surfaces involving air. Did I do this one? I kind of forget. Let me see. I probably did, right? I don't know. Now I will set up the mesh size for all the pieces involving aluminum. Aluminum, foam, aluminum. Water, air has already been set up. Water, aluminum. Okay, that's pretty much everything. So I again select all of them. Now this time I do not use 0.1. I use an even smaller number like 0.05. Height ratio is 1.05. See how that works. Okay, then I will recompute my mesh. Okay, now since I use such a fine mesh, so it takes much longer to create a new mesh. Okay, indeed it's pretty fine, although probably not as fine as I wish. Okay, but pretty fine. Okay, I believe that I now have all the mesh I need. I mean, I always have a mesh, okay, but I now probably have the desired mesh density I need. See, okay, so that's it. Okay, now I have my mesh. Okay, I also have, different surfaces which I can apply boundary conditions. I have different zones which I can apply different materials. So now it's a good time to save your project. So save your project. Then you can output your mesh. Okay. First, select the solver, which is by default Fluent. Apply. Then go here, write input. Save project first. Okay, I've already saved, but it doesn't hurt to save it again. Then select the project name. Here mine is project 2. Okay, so open. Make sure it's a 3D mesh, and you can use whatever mesh file name you want. Okay, say Fluent George. Done. Okay, done with translation. Great. So then you can open Fluent and read this mesh into Fluent. Okay, so it's .msh file, and this is the mesh file I just created. Okay. I don't know why it always gives me such interesting noise when it reads the mesh into Fluent. You can display it, although it doesn't really look very fancy. Okay. Anyways, it's just something like that. You can check the mesh quality. Make sure that you do not see any warning message or error message here. Then you begin to do the simulation, which I will show you in our next tutorial. Or you can try to do the simulation with this mesh, okay, based on a previous tutorial I uploaded, okay, because I believe I have already told you how to do such kind of simulation. Here it is almost the same thing, okay, but not exactly the same, but anyways, I will make another tutorial later.